Well, welcome to this second session of the CMIP6 analysis online poster session. I hope you came and listened this morning. We had some very good talks and got another good lineup this afternoon. So I think we can start now with Satyaban Ratna from the University of East Anglia. So Hazel, do you want to hand over to Satyaban?
Okay.
Yeah, please go ahead.
Oh, it's not going. Okay. Hello, everyone. I am Satyaban. I am going to present some of the preliminary results for the patterns of Arctic amplification in CMIP5 and CMIP6 projections. As you know, in the last few decades, the Arctic has been warming faster than the rest of the globe, which is known as Arctic amplification. Recent studies have hypothesized that Arctic amplification may impact global weather patterns over the 21st century. So our objective in the studies to diagnose and compare the pattern of Arctic amplification by analyzing the surface temperature anomaly from CMIP5 and CMIP6 models. And also another objective is to understand the influence of Arctic amplification on lower latitude climates by forcing the SST from CMIP5 CMIP6 projections in an intermediate general circulation model, which is known as the IGCM4. So here we have defined this Arctic amplification when the global surface temperature exceeds 2 degrees Celsius with respect to the pre-industrial mean. And for this purpose, we have taken or chosen 26 CMIP5 models and 13 CMIP6 models that are available to us in the SSP 2 to 4.5 categories. So we can see that in the Arctic amplification, in case of CMIP5 models, the temperature range is from 3.8 to from 6.2 degrees Celsius. And in case of CMIP6 model, out of 13 models only available, similarly, the minimum Arctic amplification is 3.8 degrees, the maximum is around 6.5 degrees Celsius. And again, we can see that in the CMIP5 models, the temperature at the end of century, we can say is a maximum up to 3.5 degree. At the same time, the maximum Arctic amplification to the end of century goes in the 8 degrees Celsius. But in CMIP6 models, some of the models at the end of global surface temperature anomaly at the in the end of 21st century, we can see that the Arctic amplification may even reach to the 10 degrees Celsius compared to the pre-industrial mean. Now we have selected 3 high amplification model and 3 low amplification model from both CMIP5 and CMIP6 models. The left panel I am showing is a CMIP5 models and the right panel is CMIP6 models for the 3 high amplification model and 3 low amplification models, the composite mean. And we can see that high amplification models, as usual, it shows warm Arctic anomaly. Even though it looks quite similar in the CMIP6, the high amplification model is warmer in CMIP5 models. But in case of low amplification model, the CMIP6 is warmer than the CMIP5 models over the Arctic regions. However, the low amplification model in CMIP5 simulates means it is a warm anomalies over the low latitude regions compared to the CMIP6. If we see the difference between the high amplification model and the low amplification model at the bottom panel, we can see that the high amplification model certainly it simulates the warmer Arctic anomaly. But in CMIP5 model C, we also see warm Arctic and Antarctic anomaly and also the warm anomaly in the Southern Ocean region. However, in that case, similarly, the difference between high amplification and low amplification model in CMIP6, we can see there is a cold anomaly in the Arctic as well as in the Southern Ocean regions. So we wanted to see the atmospheric response with respect to the Arctic amplification. We have used, as I mentioned, the IGCM4. The reference can be given is a Joshi et al. And at first we have run a control simulation with the 20th century reanalysis data from the SST we used from 1851 to 1900. And we have run two sets of Petrovich experiment. One is for high amplification surface temperature anomaly, another is the low amplification surface temperature anomaly. For the time being, in this presentation, I am showing only the atmospheric model experiment with the CMIP6 Arctic amplification composite. So we can see that I am showing the surface simulated surface temperature anomaly for the annual and summer and winter season. And we can see that the annual mean in the top left panel, the surface temperature, all the simulation, we can see the significant warming with respect to the Arctic amplification. But the high amplification experiment simulates the warm anomaly over the Arctic regions. But if we see the difference clearly between the high amplification model and the low amplification model in the rightmost panel, we can see that there is a high amplification model simulates warm anomaly in the Arctic regions and even in the Southern Ocean region. However, the low amplification model simulates the warm anomaly in the low latitude regions compared to the high amplification models.
2 minutes.
Yeah. So now we can see that if we see the bottom panel, sorry, apologies, I mentioned is a JJS, but it is actually NDJF season. So we can see that the high amplification model, which is simulates warm anomaly in the Arctic region, it is extending southward up to the 30° north, and this warm anomaly simulates seen in region, the Asian region and North America and European region. And we can see also this warm anomaly in the southern regions. Actually, this is the some preliminary analysis we did to compare the surface temperature anomaly patterns in the CMIP5 and CMIP6 models. And we, in the some more analysis we wanted to do. For example, we wanted to study the mechanism, what causes such a temperature response. And we also wanted to see what is the precipitation response in the high and low latitude regions. And we also interested to see the monsoon distributions with respect to the Arctic amplification in CMIP5 and CMIP6 model. That is what I wanted to present today, and thank you. That's the end of my presentation.
Thank you. Martin, are you online?
Thank you. Thank you for that. Thank you, Satyaban. There's a question from Matt Collins referring to these IGCM4 runs. Did you also change the sea ice extent? With the
no, we didn't do anything sea ice, but from the CMIP5 and CMIP6 model, we have used the skin temperature instead of SST, so that in the open ocean it will take as a SST, but in the sea ice region it is using as the skin temperatures. So we didn't change anything for a sea ice model in the IGCM4.
Okay, thank you. And then there's a question from Colin. In these IGCM experiments, how do you define the land surface conditions?
Land surface condition, as it is the default setup, which is can be seen in the Joshi et al. In 2015. But for this Attic amplification model, we didn't do any such changes.
Mm-hmm. Okay, thank you. Then we can move on to the second talk from Daniel Waters, and just encourage people to put questions into the Zoom chat session or the Google document, which is available for wider discussion. Okay, Daniel, please go ahead.
Okay, thank you. Good afternoon, everyone. So I'm going to be talking to you about validating the CMIP6 representation of the diurnal cycle of precipitation, and I've done that in collaboration with my PhD supervisors, Alessandro Battaglio from Leicester and Reid Allen from Reading. Okay, so the reason why we're doing a validation of the CMIP6 models for precipitation is that there's no literature currently that's evaluated their performance with regards to precipitation. So what we do is, rather than just looking at precipitation and saying, right, does the model get the same amount as the observations or the reanalyses, what we want to look at is the model able to capture the dynamics of the precipitation as well? So is it able to say that precipitation is happening at a certain time of day like the observations? Is it getting the diurnal fluctuations in precipitation correct as well? So what we've done is we've picked the CNRM model, the AMIP simulation, because it has such a fine temporal resolution of every hour, and it provides a spatial resolution of every 1.4 degrees. And we compare it with the state-of-the-art observations coming from NASA's Global Precipitation Measurement Mission. So in particular, we look at the IMERG product, which is a global gridded precipitation product. It comes from multi-satellite retrievals, so that means that the estimates are provided using spaceborne radar, spaceborne passive microwave radiometers, infrared sensors, and ground-based gauges. And the product provides the finest spatiotemporal resolution of any observation product currently available. So that's at 0.1 degrees and every half an hour, and it provides that over the past 20 years. So the methodology then for using these two products, which provide multi-decades of precipitation, is that we take the 20 years of observations and the 30 years of the model, and we match the spatiotemporal resolution of them before binning the precipitation estimates into histograms based on latitude, longitude, rain rate, season, year, and hour. And from that, for each location and the period of interest and the season of interest that we look at, we're able to get the amount of precipitation for each hour of the day. So if you look on the right-hand side here, I've shown two case studies from the observations for June, July, August. So one over the Atlantic Ocean and one over Florida in the US. And what we're looking for is to perform the analyses is certain diurnal cycle parameters. So for instance, we'll look at the mean precipitation across the day, which is represented by the magenta line. We'll also look at the amplitude of the precipitation across the day. So you can see that the minimum to maximum range is shown by the red arrows. And we normalize that by double the mean. We also look at the time of maximum and the time of minimum in the precipitation. So for instance, in the Atlantic Ocean case study on the top panel, you can see the time maximum is occurring at about 3 hours local solar time, and the minimum is at about 20 hours. And we also want to characterize the diurnal cycle by the number of peaks that are shown as well. So for instance, the Florida US case study is a very nice bell-shaped curve, which only demonstrates one peak and one trough, whereas the Atlantic Ocean case study is a little bit more noisier. It has two distinct peaks and troughs, and to make sure that we're not capturing kind of noisy peaks, like for instance the one that you might see at around 12 hours, we put a criterion on based on the prominence and the width of the peak to make sure we're just capturing the kind of true ones. So for the analysis, what we ended up doing is we used June, July, August, and we used the whole period from the IMERG observations, so about 19 years, and we used 29 years from the model. The reason why we did this rather than use the 8-year overlapping period from 2000 to 2007 was because the results are pretty much the same, and the advantage of using the longer period is that we get rid of a lot of the noise in the global analyses. Sorry, I think I skipped one slide too far. So the top two panels that I show here are the observed mean precipitation across the globe. And then on the right hand side, I show the CNRM AMIP simulation minus the observations. And the black dots are just to highlight where there's arid regions in all the plots. So for these regions, we consider the diurnal cycle here not to be strong and not to be considered too thoroughly. So for instance, what you can see is when we compare the mean precipitation from the model to the observations is that the differences tend to be the strongest across the intertropical convergence zone, and arguably over land there tends to be more underestimations by the model, and over the ocean there tends to be more overestimations. Then looking at the number of peaks in the diurnal cycle, from the observations, you can see that in June, July, August, the northern hemisphere is summertime and the southern hemisphere is winter time. So in this kind of summertime hemisphere at the north, we're able to see that the diurnal cycle tends to have one peak over the ocean and over the land. And when you go into the winter time, the observations suggest that the diurnal cycle tends to have more peaks, 3 or 4 peaks in some cases. And in comparison with the model, suggests that the model is doing quite good in mapping the number of diurnal peaks that we see for land and ocean in the summertime in the tropics, but in the southern hemisphere, the winter, it suggests that there tends to be less peaks than is seen by the observations.
2 minutes, Daniel.
Okay, thank you. And then the other two parameters that we considered were the diurnal amplitude. So you can see from the observations that what you tend to find is that over land, the amplitude of the diurnal cycle is a lot larger, so it can exceed 60% of the mean in a lot of places. And then over the ocean, it tends to be a lot more muted, the amplitude. It's typically stronger in the summertime season, which you can see kind of near the Gulf Stream, where the arrow is. And then in the southern hemisphere, the diurnal amplitude tends to be a lot smaller. And a comparison again with the model shows that the model tends to do a fairly good job on the amplitude. So over the oceans, it tends to mostly capture the amplitude coming from the observations. Over land, there tends to be some more issues with typically underestimates in the amplitude. But kind of a key area to note is the Amazon region, where it actually overestimates by quite a lot, so up to 60% of the mean, larger than the observations. And then we finally considered the time of maximum from the observations. In particular, the places to focus here are the regions where the amplitude is quite large, because this is where we're seeing a real strong diurnal signature. So it's quite clear that over land we tend to see kind of evening time maximum in precipitation, whereas over ocean, and in particular in the strong diurnal cycle regions, you can see that we tend to see kind of late morning, and in coastal regions we tend to see kind of noon. And the big kind of finding from the study then is that you can see from the comparison with the models and the observations is that the model tends to lag behind the observations by around 6 hours, sometimes more in some cases, and in some places it can go as far as being 12 hours behind. But over ocean it tends to do a slightly better job. And in terms of future work, what we might look at is the dynamical signatures from so looking to see the convection and in particular trying to remove some of the intraannual variability coming from, say, stratiform cases. So just focusing on the convection in particular. Okay, thank you for listening.
Sorry, I'm having difficulties unmuting Martin. Hang on a sec.
No problem.
Martin, can you try yourself and see if that works?
It does now.
There
It
we
didn't
go.
work a minute ago. Okay, thank you, Bobby. Thank you, Daniel, for that. I've got a couple of questions in the chat channel. Let me see. So Colin is asking, is it possible to use satellite data to do a similar evaluation of model cloud fields and their radiative impact?
So that would be using another satellite. So the one that we use, the Global Precipitation Measurement Core Observatory, that only looks at the precipitation in particular, whereas you'd be looking at using the CloudSat, satellite. That will be able to give you information on cloud fields, but the time period for the cloud data set is typically shorter.
Yeah. Okay. There are a few other questions in chat. I'll just take two together from Kath Senior and Peter Cox, which are you thinking of doing this analysis for a wider range of models, and would you expect to see similar results from other models?
Yeah, so what we're hoping to do is to perform this analysis for further models. So what we started with was the model which provided the finest kind of temporal resolution so that we could do a good analysis with the observations. And we were keen to look at the AMIP simulations in particular. So what we might do now is look at kind of analysis, maybe using some of the other different types of deck simulations. But what we're keen to do is to keep the temporal resolution from the model quite low. So ideally, we're looking at data that's provided every hour or less. But yeah, the hope is to do further models.
Yeah. Okay, great. Thank you. There are other questions, so maybe that can be covered in the Google Doc or offline. And now we can move on to Till Kuhlbrodt from University of Reading. So over to you, Till.
Yeah, thank you, Martin. So I'm going to have a look at the historical ocean heat uptake in some of the CMIP6 Earth System models. So we're looking at ocean heat uptake, just a little motivation, because with the current radiation imbalance at the top of the atmosphere of about 1 watt per square meter or a little bit less, a lot of additional energy is stored in the Earth system, and we know that 92% of this additional energy are being stored in the oceans. That is since the early 1970s. So these are huge amounts. The latest estimate, which is this blue star up here, for the total Earth system warming 1971 to 2018 is 400 zetajoules, and that's 10 to the 21 joules. So this is a plot based on the observations, and this talk is mainly about how good the models, the CMIP6 models, are at reproducing this observed ocean warming. I'm looking at 4 of the CMIP6 models, and that's UK ESM 1.0 and HEGM 3 GC 3.1 LL, which have both the same spatial resolution, and CNRM ESM 2.1 and CNRM CM6.1, and they also have both the same spatial resolution. All 4 of these models have exactly the same ocean model, NEMO 3.6, ORCA 1, So that's exactly the same model. Between the French and the UK models, the settings might differ very slightly, but basically the same model. We know from CMIP5 that there was quite a wide range across the models in reproducing this warming, but the ensemble mean did the job quite well and was close to observations. So here we see what happens in the models. On the right, the two UK models in red and green. On the left, the two CNRM models in blue and yellow. The top plot shows the TOA net radiation balance here from 1900 to 2015. That's normalized with respect to the PI control run of each model. And then here in these two lower panels, we see the historical ocean heat uptake, and that is full depth. So this is global ocean heat uptake for the entire global ocean. We see here in black and purplish, this is various observational data sets. The simulations are normalized to the year to the period 2005 to 2014. The lower panel is just a zoom in. The middle panels have the year 1900 to 2015, and the lower panels is just a zoom in 1955 to 2015. So we see here for the UK models, both of the UK models are actually quite similar. The bold lines are the ensemble means, and the thin lines, a bit blurred here on the zoom, are the ensemble members. And we see that after the early 90s, the temperature rise here is a little bit faster than observations, but certainly within the range. Before mid-1970s, and there's basically no ocean heat uptake simulated in the UK models, even though the observations suggest here between the 60s and 70s, something like 70 zettajoules. If we look at the CNRM models compared against exactly the same observations, then we see that they are doing a much better job here at being close to observations, especially here before the 1990s, where here an ocean heat uptake is actually simulated as opposed to the UK models. However, after 1990, the warming rate, heat uptake rate is here smaller than observations, where it is here larger at observations. Interestingly, this matches what we know about the equilibrium climate sensitivity, which in the UK models is higher than in the CNRM models. So this matches the stronger temperature rise. And for the aerosol forcing, we know that the CNRM ESM2, which is the yellow model here, that has the smallest aerosol forcing, smallest in the sense it's a negative number, but it's a negative number that is closest to zero, whereas it's stronger here in the UK model. So this suggests that before 1990, the aerosol forcing has an impact. After 1990, the TCR, or equivalently the greenhouse gas forcing. If we look at the regional ocean heat uptake, to go away from the global to the regional perspective, we see here the ocean heat uptake in the top plots 0 to 700 meter, bottom plots 0 to 2000 meters. Left hand is 1971 to 1991, on the right hand side 1991 to 2014. And if we see what the models are doing here, 0 to 700 meters in the 70s and 80s, the UK models in red and green have an ocean heat uptake that is far too small across all basins. CNRM models get it much better, maybe a little bit too warm in the Pacific, actually.
2 minutes till.
Yeah, thank you. And then after 1991, we see that there's way too much warming in 0 to 700 meters in the UK models, especially in the Atlantic. So this shows that these two models, two groups of models, UK and French, even though they have different, the same ocean model, but they have definitely different preferred regions for ocean heat uptake, either the Atlantic or the Pacific. And if we zoom further into one of the models, this is the UK Earth System model. And here we look at the depth profiles. So this is just temperature change, not ocean heat uptake, for the 6 individual basins, Northern, Southern Hemisphere, Atlantic, Indian, Pacific, and globally. And then we see that the UK models tend to match the warming in the top 200 meters. The UK ESM ensemble cools in the top 1,000 meters below that, where the observations warms, and then it's the opposite in the abyssal ocean, where the simulations warm and the observations suggest a cooling. There is an enormous warming here, so this is all detrended simulations. This is so we do not see the underlying model drift here. There's an enormous warming here in the North Atlantic. That's from ocean heat uptake in the North Atlantic and being transported at depth by the AMOG. And we also see here a very strong ocean heat uptake in the South Pacific from intermittent deep water formation events here that comes with a very large variability there. And we also see here a tendency for a mid-depth cooling here in the top 500 meters, which is mostly to see here in the Southern Ocean, in the Southern Hemisphere. So to conclude, we see that so the hypothesis here is that the aerosol forcing and the greenhouse gas forcing directly have an impact on these ocean heat uptake rates, and it's quite varied across the different models, even though the ocean model is actually the same. And that's where I'm going to stop. Thank you.
Okay. Thank you, Till. That's good. Got a few questions. One is from Yevgeny Aksanov at NOC. Is there a potential effect of the two different sea ice models used in the UK and French simulations?
That's a very good question. I would say I would not expect that, actually, because because we see that a lot of the ocean heat uptake actually happens away from the seasonally sea ice covered regions, and a lot of the relevant differences. And so I would not expect that, but we haven't looked at it specifically.
Yeah. Okay, then I'll just take a question from somebody who hasn't asked anything yet, from Pat Hyder, saying obviously the atmosphere models are very different, and you mentioned that the NEMO model is used in both, but is the model configuration the same in both, particularly vertical mixing, isopygnal mixing, and other setups?
So the model configuration is not exactly the same. There might be there will be smaller differences, but we know from sensitivity studies with the NEMO or Orca-1 configuration that varying these mixing parameters, for instance, does not have a strong impact on the global ocean heat uptake. It might have impact regionally and confined in time, but not for the centennial global picture.
Okay. Thank you very much. There are a few more questions, so please follow that up in the Google document if you can. And now if we can move on to Rebecca Varney from University of Exeter. Over to you, Rebecca.
Okay, thank you. I don't seem to have control yet, so just wait.
It takes a minute for it to get across.
Okay, great. Oh, right now I still don't have it. Okay. So in this presentation, I'm going to be presenting a new spatial emergent constraint that we found on the sensitivity of soil carbon turnover to global warming. So the aim of this constraint is to reduce some of the uncertainty associated with the feedback from soil carbon to climate change. So how soil carbon is going to respond under climate change will be determined by two main components. So one, the increased input of carbon into the soil from vegetation, and two, the increased output of carbon from the soil from respiration. And these two effects counteract each other in terms of the overall effect of soil carbon in the future. And both are uncertain and both are poorly constrained. So in this study, we consider the latter, where this increased carbon output is due to, under increased global temperatures, increased microbial activity results in greater rates of decomposition, meaning more soil, more of the carbon, is released into the atmosphere from the soil. So to isolate this effect, we define a soil carbon turnover time, which is the residence time of carbon in the soil. And this is defined as the ratio of soil carbon to the outputs, which is heterotropic respiration, which is this microbial respiration that I just talked about. So the soil carbon turnover time is predicted to decrease exponentially with warming. However, there's a large uncertainty associated with this, and which is what we set out to reduce. So, and obviously a reduction in the uncertainty in the soil carbon turnover time will be a reduction in the uncertainty in the resultant change in soil carbon. So the uncertainty in this resultant change in soil carbon is pretty evident when you look at the spread across the CMIP6 models, which you can see on this figure on the graph. So we've got this change in soil carbon against temperature. So even at 2 degrees warming, there's a big spread in the models, and yeah, so this uncertainty is quite important because these are key components of uncertainty in the global carbon budgets for the Paris Agreement targets. And this uncertainty has actually existed across CMIP generations, and if anything, CMIP6 is actually more uncertain than CMIP5, which is why we set out on this new method to try and reduce this uncertainty. So we're talking about spatial emergent constraints. So a spatial emergent constraint is the idea of using a spatial temperature sensitivity to constrain a future response to warming. So the idea is if the spatial temperature sensitivity tells us how sensitive something is to temperature, we can use this to constrain the future warming response. And in this case, we're considering soil carbon turnover time, which we call tau S. So first we need some data for this. So we consider observational soil carbon and observational heterotropic respiration, which are the two top maps. And then from this, using the equation, we deduce an inferred soil carbon turnover time from observations. So to investigate the temperature sensitivity of this, we plot against temperature, where the black data here is each latitude and longitude, and the thick black line represents the relationship between these, so between soil carbon turnover time and temperature. So this black line represents the spatial temperature sensitivity of the soil carbon turnover time. And we can do this for each of the models in CMIP6 to obtain model-specific relationships, which are plotted on by the colourful lines. And you can see that there's large variations amongst the models and with the observations. So clearly this inability of the models to reproduce this temperature sensitivity is the reason for a lot of this uncertainty in this soil carbon response. So the premise of the constraint is if we can use this correct real world sensitivity to constrain the response of soil carbon in the future. So to test whether this is a valid thing to do, we test with our CMIP6 model ensemble, where we calculate the change in soil carbon using the equation. However, on this graph we calculate this using two different methods to calculate tau and compare the results. So on the y-axis, we've got the change in soil carbon due to the change in soil carbon turnover, calculated using model output, so just the model output variables. And then on the x-axis, we calculate this change in soil carbon turnover. However, this time we calculate the change in soil carbon turnover time using the relationship to temperature alone. So we calculate the change, giving this relationship future temperature and present day temperature. And then comparing how well this predicts compared to the models in this figure, you can see it actually does a pretty good job, and all of the points, regardless of SSP, are all tightly hugged around their 1-to-1 line. We've got an R-square value of more than 0.9 here. So with this in mind, this allows us to think of our constraint. So this time we've got this a very similar figure. However, this time change is for 2 degrees warming, and then we can calculate. We can calculate the x-axis again. So we consider the temperature spatial relationship derived from our observations to represent the real world sensitivity, and we can use this to calculate a change in soil carbon. So given it future model temperatures from each of the CMIP6 models, because obviously we don't have observational future temperature, we can calculate a change. And then following up to our emergent relationship and following across, we can end up with a constraint on the y-axis, which is a constraint on the change in soil carbon as a response of tau on the CMIP6 model ensemble. And this has successfully reduced the uncertainty from 112 petagrams of carbon to quite significantly reduced to 33 petagrams of carbon, with a mean of 180 petagrams of carbon released from the soil at 2 degrees warming from this effect. So yeah, thank you, that's everything.
Thank you, Rebecca.
Right, thank you very much, Rebecca. So we've got a couple of questions. One from Chris Jones. Can you account for very large differences in the initial carbon pool size and therefore huge differences in their control state turnover times? It looks like you're working on delta carbon, but the initial pool size is very different.
Yeah, we do. I haven't got the plot on the slides, but I did investigate this. So the first initial plot where I investigate the projected change in warming, I divided each model by the initial soil carbon stocks, and it had a little bit of effect, but the sensitivity still remained, and it didn't make a huge difference. So we did take that into consideration. And obviously, when you consider observations, obviously the initial soil carbon in the real world is kind of accounted for, if that answers the question.
I think so, yeah. Thank you. So I had a question about that. You copied on your initial plot showing the spread of models in the change in soil carbon, but they look to me to cluster into 3 groups. I wonder if there's any families of soil models which could explain that clustering.
Yeah, I haven't looked into that, but that might be a good point. I can't remember the order of the models, but maybe they're used as similar land surface models. I'm not sure. Okay. I can look into that.
All right. Thank you. Then I think we should move on to the next talk. So if Hazel can hand over to Paul, and so this is Paul Ritchie on identifying potential abrupt shifts of Amazon rainforest dieback in the CMIP6 dataset.
Okay, thank you, Martin. So today I'm going to present some work that's still very much in progress, and it's joint work with Peter Cox and Joe Clark. And it's our search of the CMIP6 dataset for potential abrupt shifts of Amazon forest dieback. And dieback of the Amazon rainforest is one of the recognised policy relevant tipping points in the climate system, as identified by Tim Renton and others back in 2008. When we say tipping point, what we mean is where we see a small change in input levels leading to large qualitative changes in the output of the system. So to search for these potential abrupt shifts of dieback, we're going to be looking at the tree cover from 4 different models from the CMIP6 dataset, using the 1% per year CO2 increase experimental runs. And we want to use these runs in particular because any abrupt shifts that we find, we want to know that they're climate driven as opposed to land use driven, for example. Okay, but before we go into actually looking for the abrupt shifts, let's just analyze what changes we see in these runs. So like I said, we've got 4 different models, each model in its own separate row. And then our left column is our starting tree cover for the 4 models. And as you can see, there's quite a range spread of initial states for this tree cover. In particular, the GFDL model in the second row gives a very patchy and unrealistic starting state, but as you'll soon see, it does actually give us some interesting results. Now in the middle column is our absolute change from this starting tree cover by the end of the run, or equivalently when we've reached quadrupled CO2. And you notice in the top panel, the EC Earth model, we have this widespread dieback of tree cover. And maybe this isn't too surprising due to the high climate sensitivity that the model has. But generally there's the agreement that we see dieback of tree cover in central and southern parts of the Amazon, with small bits of growth maybe in the northeast. But also what was a very surprising result for us was the UK ESM result, where there's very little change in tree cover. And this is despite the model having a very high climate sensitivity. Now on the right column, what I've done is plotted the factor of CO2 increase for which tree cover reaches its maximum. And so what's of particular interest is there seems to be an optimal level of CO2 for which tree cover reaches its maximum. In particular, these orange and yellow regions indicate tree cover would reach a maximum at around 600 parts per million before decreasing again. So now that we've seen what changes might happen, are any of these due to abrupt shifts? So for something to be an abrupt shift, it has to fill 2 criteria. The first one we impose is that the tree cover has to change by at least 10% when we fit a linear regression through any 15-year period. And then this abrupt shift has to contribute to at least 25% of the overall change. Now, this left column of maps shows the amount of the abrupt shift. And again, we've got red colors to denote a decline in tree cover and a green to denote increase in tree cover. And then the stronger the shading, the stronger the abrupt shift. Now, the first thing you might notice is that we detect abrupt shifts nearly everywhere in the EC Earth model. But when we actually looked into this in a bit more detail, what we found is that a lot of these abrupt shifts were due to the high variability within the model. So what I've tried to do is put on some boxes on these maps to identify regions of interest where either there's a significant change in the resulting from the abrupt shift, and or the abrupt shift happens at roughly the same time. Again, so this right column is indicating the factor of CO2 increase at which the abrupt shift occurs. So you can see a lot of these ones here, for example, occur at 2 times CO2. Now, also in the GFDL model, we get, despite the patchy initial state, we do have quite a few regions of interest where there's these abrupt shifts. But this is less for the MPI model. And again, for the UK ESM model, we don't have any abrupt shifts at all. Now you can see, so across these models, some models predict a lot of abrupt shifts, some not so much, but there's no coherent structure amongst models. There's no one particular region where we can say a lot of models, or the majority of models, predict an abrupt shift. That just doesn't exist. But let's look at some of these cases in a bit more detail. So here we take one box and we take the domain average within this box and plot the temperature in red and the precipitation in blue in the top panel. And in the bottom panel, we plot the tree cover. So if we work clockwise, starting in the top left, this is an example from the EC Earth model. And what you'll notice is that we have this initial increase in tree cover, reaching an optimal CO2 concentration of around 400 parts per million, so roughly around present day conditions, before then slowly declining and then hitting this abrupt shift at around 600 parts per million. But if we look at the drivers, what you might notice is that just before this abrupt shift, we have a sudden drop in the precipitation, which might be a key driver of this abrupt shift. Now, on the top right is an example from our GFDL model. And what you can notice, again, is we've got this very nice initial steady state, but then we have this sudden drop followed by a quick regrowth period at around 700 parts per million. Now, if we look at, again, the temperature and the precipitation, again, what you might notice is that before this abrupt shift, you've got a sudden increase in the temperature and also a sudden decrease in the precipitation. And what this might indicate is that the conditions are more susceptible to fire events, so this might well be a fire-triggered and abrupt shift. And likewise, after this regrowth period, we might have another fire-triggered event at around 800 parts per million.
2 minutes.
Okay, thank you. But then when we, what we find at the end of the run is possibly what's like a more conventional abrupt shift, but note it's for really high CO2 concentrations. Now in the bottom right panel, we've got an example from the MPI model. And this is where we actually didn't detect many abrupt shifts. Not even all the grid points within this box are actually have abrupt shifts. So when you take the domain average, we get a smoothed out time series where you wouldn't say there's a particular abrupt shift, but despite there being individual grid points which do have abrupt shifts. But again, what's good to note here is that we have this optimal in the CO2, optimal tree cover at around 600 parts per million in the CO2 concentration. And then finally, bottom left panel is again another example from the GFDL model. And this is a really nice example of where we have an abrupt shift that doesn't seem to be triggered by fire because there's no obvious causes from the temperature and precipitation time series. So maybe this abrupt shift could be actually a tipping point example. And so thank you for listening.
Yep. Thank you very much, Paul. We've just got time for a couple of quick questions. One from Rachel James. Why is the starting tree cover so different between models?
I don't know exactly. I believe I still need to actually probably contact someone from the at least GFDL community and check whether, I'm sure these runs do seem to have fire, and so that might be a cause of the original starting condition of the GFDL model for it being so patchy, but yeah, I'm not too sure.
Mm-hmm. And there's one from David Stevenson. I thought routing depth was the important parameter. Is this handled differently between models, or isn't this the important thing?
Routing depth. Yeah. Okay, might be. I have wondered about this. These quick regrowth periods where I guess they might be newly developed trees, and so therefore the root depths won't be so great there. It's definitely something that I can look into. So yeah, thanks for your suggestion.
And just one from Jeremy Walton. Can you see any examples of warming and of fires that are not linked to abrupt shifts?
I have, yeah, so that'd be probably the next step in this work, is to actually try and detect abrupt shifts in the climate drivers, and then look at, do the reverse analysis, I guess, look for abrupt shifts in the climate drivers, and then see what the true cover time series looks like. So no, I still need to look at that.
Okay. Well, thank you then for that, and we're at the end of the hour, so thanks again to everyone, to all the speakers for some very interesting talk, to Hazel and Poppy for looking after the session and managing the Zoom, and for Colin and others for organising these meetings. And we can meet again at 11 o'clock tomorrow morning, so please come back for more tomorrow.